So I'm now going to continue this business about these tors being equivalent. Okay, so we had the notion of acyclic complex was where the homology was 0. We had a notion of quasi-isomorphism, okay, and that's where they have the same homology. Okay, this is resolution was example of something that was quasi-isomorphic. Exact sequences were examples of acyclic complexes. Okay, then we talked about shifting and what it had to do with suspension. Okay, suspension is something that moves the index of homology, and just like that, the incarnation of suspension in chain complex land is the shifting map. So the shifting map, where you do this little angle, or the square brackets 1 is where you move the complex just over to the left by 1. Okay, and then I showed that the shifting for homology and cohomology were compatible if you use this index switch convention. Okay, that was something that I was worried about. All right, so to talk about, in order to attack the thing where we're trying to show that tor can be both a left-derived functor and a right-derived functor, or sorry, a left-derived functor where you take a resolution of B, or a left-derived functor where you take a resolution of A, what we're going to need to do is we're going to need to do a resolution of A and B at the same time. Okay, and to deal with that, we have this notion of a double complex. And double complexes are pretty important, and double complexes and total complexes. Okay, so let's take a double complex. Double complexes and total complexes. Okay, so I'm going to okay, so what is a double complex? So a double complex, a double chain complex, right, is well, it looks like here we have a bullet, and then we have a vertical map, and then we have a horizontal. We have a bunch of horizontal maps, and we have a bunch of vertical maps. Okay, so let me kind of just draw this out. So you have Aij. Okay, now I'm going to do homology. So we're going to go AI minus 1j, AI plus 1j. Okay, and this keeps going, and this keeps going. Okay, and then we're going to go down here. So AI minus 1, j minus 1, AI j minus 1, AI plus 1, j minus 1. Okay, so we have arrows going this way. So it's just like a chain complex in two directions, or a bunch of chain complexes. Okay, and this keeps going. All right, and then this goes AI plus 1, j plus 1, AI j plus 1, AI minus 1, j plus 1. All right, so we have arrows going down. We have arrows going this way. And then we're to keep going like this. All right. And then maybe this keeps going as well. Okay, so we have these things where, okay, so these things, so dv, dh, so these vertical ones are going to be the dv's, and these horizontal ones are what I'm going to denote by the dh's. So where dv dh is equal to dh dv. So I'm going to just ask that they commute. Some people ask, so one of the conventions that there's two conventions. So some people will ask that they commute, some people will ask that they anti-commute. And depending on your convention, your total complex will be different, and I'll get to the total complex in a second. Okay, so we have dh squared is 0, and dv squared is equal to 0. Okay, so this is what a double complex is, and then the morphisms are going to be our chain morphisms. Okay, so these are going to be like maps. So these are going to be maps Aij to Bij. Let's call this Fij. That commute with the D's, with dV and dH. Okay, so yeah, so you just take, it's just like a chain complex, except for you just kind of have it two ways. Okay.
You have to move to 3D, right?
You could do a 3D version of this, right? But
I mean, if you were to draw out the B sub ij's and draw the maps, you would have to kind of, anyways.
Yeah, exactly. Yeah, if I were gonna have to do the, if you were gonna draw the B sub ij's, you'd have a big lattice thing. You'll have like a big, it'd be a 3D thing. Yeah, that's correct. Yeah. Okay. Okay. So, so here's some exercises. So exercise. So one is that actually chain complexes here of modules. These are an abelian category. And the other thing is that so you have to figure out what the kernels are of this thing and what the quotients are, right? So the exercise here is figure out kernels and quotients. So what are you allowed to mod out by? Okay, so so the things that you're allowed to mod out by are the things where the maps work. So this is the usual chain complexes. And then if I do chain complexes, so chain complexes make sense for any category. So this category here, if I take chain complexes of chain complexes, this is equivalent to double complexes. Okay, so these are again chain complexes with chain maps. All right. So yeah. So this, another way to think about double complexes are chain complexes of chain complexes. Okay. So okay, so there's a functor that I want to talk about. So this is what a double complex is, and so there's a functor. So called totalization. Totes. Okay, and it takes okay, so maybe we should call this, we should give this this category a name. So let's call this category okay, this term, so notation. Okay, so let's call this choose squared, and then we need to do for a category. So for concreteness, let's do the category of our modules. Okay, so this is the category of double complexes. Okay, and then of course you can make a category of cochain complexes, but I'm not gonna, the same thing, except for you just reverse, you use the indexing switch convention. Okay, so there's a functor here from double complexes to usual complexes. Okay, which I want to describe. And so so this is the totalization functor. This is called totalization. Okay, and what does this thing do? Okay, so what it does is it takes this thing, and let's take a chain complex. So let's do a bullet. Okay, and let's look at the nth degree. And so this thing is the direct sum of I plus j is equal to n of ai j. So this is the chains here. Okay, so so we take a double complex and it maps it to this thing, and the D map here, totalization, right? And then So we can do it on a particular summand, Aij, right? So this thing is -1 to the j. Then we take the vertical part plus the horizontal part. Okay, so this is what I was saying about the sign convention. So to get d squared is equal to 0, right, you'll either need to define your chain complexes, your double complexes, to be anti-commutative, right, where you don't have this but you have a minus sign, or you're going to need to define your total complex, your total differential, to have this sign thing here. Okay, so so an exercise is to check that I didn't mess up the sign convention. The sign convention, and fix it if I did. Okay, so so I think this is correct. But yeah, you just need to check that d squared is equal to 0. And note that this is just on one component, right? Really, you're going to have a bunch of pieces, right, that you put together. Okay, so there's another video that I have too that's on spectral sequences that goes over this again in a little bit more detail. Okay, and so what's one way to get a double complex and to get a total complex? Okay, so let's do the main example. There are lots of ways to get double complexes. They're pretty ubiquitous. So, you know, yeah, lots. Yeah, I want to say like all spectral sequences I know come from this. Yeah. So that's for another video. So so let's do this. So given a chain complex. Okay, I'm gonna start dropping the bullets again because it's gonna be kind of annoying. Okay, so this is A ends, and B. This is B bullet. This is BN. BN. Chain complexes. We can form a double complex. Okay, maybe add something else to make something else to the okay, and then the other thing that you should check is check that the totalization is functorial. Okay. Okay. So that chain maps map to chain maps. Okay, so given it, so we can form a double complex. So here's the double complex. So this is going to be of R modules, let's say. So now this kind of matters because we need a tensor product. Okay. We can form a double complex where we do A tensor RB like this. And then if I do this, and okay, so this is a new chain complex inside. This is a double complex. Maybe I should, for emphasis, let's do that. Okay, and let's take the nth, okay, and let's take the nth component of this thing. And so this is going to be AN tensor BM. Okay. And so this is a double complex, and the signs need to be flipped a little bit. Or actually, I think this is good. This is good. This is fine. Okay. because we defined our double complexes to be chain complexes in both directions. Okay, so this is our double complex. Okay, so where we do this thing, and the D vertical is just the so D vertical is D on A tensor with, okay, let's do the nth one, BM, and D horizontal on the nth piece is going to be AN tensor with D, B, and then we take the nth one here. Okay, so this is going to be our double complex. And then from this we can form the total complex. Okay, and then this is going to play a role in what I have to say next. Okay, so the total complex here will be like, so what you do is that if you take the total complex, right, of just for concreteness, A tensor B of N, so this is the direct sum of I plus J is equal to N, AI tensor BJ. Okay, so this thing is the total, this is the pieces of the total complex. Okay, so you can take two chain complexes. So if we had two resolutions, right, I can make a total complex out of those things. Okay, so now I want to talk about mapping cones. All right, so now we have this thing. Okay, so there's this crazy complex that we have. We have this thing from